Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is part 4 on derivatives and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view parts 1, 2, and 3 on derivatives prior to watching this video. In this video, we will be discussing trigonometric limits, derivatives of trigonometric functions, and derivatives of inverse trigonometric functions. To uncover the derivatives of trigonometric functions, we must first understand these limits. The limit of sine x over x as x approaches 0 equals 1, and the limit of cosine x minus 1 over x as x approaches 0 equals 0. The easiest way to understand these limits is graphically. Let f of x equal sine x. To take the derivative of sine, we first start with the definition of the derivative. Then we insert f of x equals sine x. Using the sum formula, sine of x plus h equals sine x times cosine h plus cosine x times sine h. Next, we group the first and third terms and factor out sine x. Next, we split the limit at the plus sign. Since we are taking the limit as h approaches 0, sine x and cosine x are constants and can be pulled out of their respective limits. What is left of the first term in the limit is the cosine definition we previously discussed, which equals 0. The second term is the sine definition, which equals 1. Taking the limits results in sine x times 0 and cosine x times 1, so f prime of sine x is cosine x. Let f of x equal cosine x. To take the derivative of cosine, we first start with the definition of a derivative, and then insert for f of x equals cosine x. Using the sum formula for cosine x plus h equals cosine x times cosine h minus sine x times sine h. Next, we group the first and third terms and factor out cosine x. Next, we split the limit at the plus sign. Since we are taking the limit as h approaches 0, the negative sine x and cosine x can be removed from their respective limits. What is left of the first term in the limit is the sine definition, which equals 1. In the second term, we have the cosine definition, which equals 0. Taking the limits, we are left with negative sine x times 1 and cosine x times 0. So the derivative of cosine x is negative sine x. Let h of x equal tangent x, and let's find the derivative. Because tangent x equals sine x over cosine x, we can use the quotient rule. For this, we let f of x equal sine x and g of x equal cosine x. F prime of x will then equal cosine x, and g prime of x equals negative sine x. Next, we fill in the values of the quotient rule. The numerator can then be simplified to cosine squared x plus sine squared x, and the denominator is cosine squared x. Cosine squared x plus sine squared x equals 1, so the derivative equals 1 over cosine squared x, or secant squared x. The derivatives of other trigonometric functions may be solved in a similar manner. d dx of secant x equals secant x tangent x. d dx of cosecant x equals negative cosecant x cotangent x. d dx of cotangent x equals negative cosecant squared x. Let's take a couple of sample problems and find the derivatives. First, let f of x equal x sine x. For this, we use the product rule. So we take the derivative of x times sine x plus x times the derivative of sine x. The derivative of x is 1, and the derivative of sine x is cosine x. So we are left with f prime of x equals sine x plus x cosine x. Next, let f of x equal e to the x cosecant x. Again, we use the product rule, taking the derivative of e to the x times cosecant x plus e to the x times the derivative of cosecant x. The derivative of e to the x is e to the x. The derivative of cosecant x is negative cosecant x times cotangent x. Our final answer is then f prime of x is equal to e to the x cosecant x minus e to the x cosecant x cotangent x. Next, we'll look at the inverse trigonometric functions, starting with f of x is equal to the inverse sine of x. This can also be called the arcsine of x. If we write the function as y equals the arcsine of x, it can be rewritten as x is equal to sine of y. From this equation, we can relate x and y as parts of a right triangle, making y one of the two non-right angles. Since sine is the opposite of the hypotenuse, then the opposite side is x and the hypotenuse is 1. Next, we use implicit differentiation to find the derivative of x is equal to sine of y and get 1 is equal to cosine y dy dx. If we solve for dy dx, we get 1 over cosine y. We then refer back to the triangle and use the Pythagorean theorem to get the adjacent side, which equals the square root of 1 minus x squared, and replace cosine of y. So the derivative of arcsine of x is 1 over the square root of 1 minus x squared. Next, we're going to solve for the arc cosine in the same manner. We rewrite y equals arc cosine x as x equals cosine y. On the triangle, this makes the angle y, the adjacent side x, the hypotenuse 1, and the opposite side the square root of 1 minus x squared. Differentiate implicitly to arrive at dy dx is equal to negative 1 over sine y, or dy dx is equal to negative 1 over the square root of 1 minus x squared. Solving for the arctangent in the same manner, x equals tangent y, which puts y at the angle, making the opposite side x and the adjacent side 1. This makes the hypotenuse the square root of x squared plus 1. When we differentiate implicitly, we get 1 equals secant squared y dy dx. Solve for dy dx to get 1 over secant squared y, or cosine squared y. Referring again to the triangle, cosine is the adjacent over the hypotenuse, or 1 over the square root of x squared plus 1, which, when squared, comes out to 1 over x squared plus 1. We can use the same techniques to find the derivatives of the other inverse trigonometric functions. d dx of arcsecant x is equal to 1 over the absolute value of x times the square root of x squared minus 1. d dx of arc cosecant x is equal to negative 1 over the absolute value of x times the square root of x squared minus 1. d dx of arc cotangent x is equal to negative 1 over 1 plus x squared. As a sample problem, let's start with f of x is equal to the arcsine of e to the negative 2x. In this problem, we'll use the chain rule. Let u equal e to the negative 2x. This would make y equal arcsine of u. du dx would then be negative 2 e to the negative 2x, and dy du equals 1 over 1 minus u squared. du dx times dy du would then be 1 over 1 minus u squared times negative 2 e to the negative 2x. When we replace u, we got our final answer, dy dx equals negative 2 e to the negative 2x over the square root of 1 minus e to the negative 4x. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.